Okay, so welcome you, all of you. Hope all of you are well.
Yes, sir.
আচ্ছা কেমন আছেন আপনি?
ভালো। তোমরা সবাই ভালো আছো তো?
আচ্ছা
হ্যাঁ স্যার।
আচ্ছা।
Hey,
So,
Shumon.
okay. So I will discuss about the 8086 microprocessor today. Okay. So in that time, when I would like to lecture, so don't interrupt me or don't disturb me in any way. Okay. So actually, I will mute you all. So after delivering my lecture, then 10 minutes will be there. Within 10 or 15 minutes, we'd like to discuss about some doubts or some queries regarding the topic. Okay. But within delivering my lecture, in that time, I would like to meet you all. Okay. So if you have any queries, any doubt, so ask me after that. Clear? Clear to all of you? So all of you have got the link of this meeting? I think so.
Yes, sir.
Because everyone is not connected to the Google Classroom. So do you have any information regarding the absentees? What happened? What is the problem? Sir? Sreyashi? Are you here? Sreyashi?
আচ্ছা আচ্ছা
So is there any problem regarding the joining into Google Classroom?
স্যার কথাটা আসছে না, বুঝতে পারছি না ওয়ে।
কোনোভাবে তাদের সাথে কন্ট্যাক্ট করা যায়নি, মানে do you have given the information that all of you must connect with the Google Classroom so that when I
ওকে স্যার, আমি গ্রুপে জানিয়ে দিচ্ছি, এক্ষুনি গ্রুপে জানিয়ে দিচ্ছি।
একটু জানিয়ে দাও। তো কারণ আমি সব লিংক, এই মিটিং এর লিংকও আমি ওখানেই পোস্ট করেছি, তো যদি ওখানে কানেক্ট থাকে
আচ্ছা জানি, হ্যাঁ
দেন তারা এখানে জয়েন করতে পারবে। ঠিক আছে। এবং
হ্যাঁ স্যার, আমি এক্ষুনি জানি।
যা কিছু অ্যাসাইনমেন্ট বা টেস্ট যদি কিছু নিতে হয়, সো আমি ওগুলো কিন্তু গুগল ক্লাসরুমের থ্রু দিয়েই নেবো। হ্যাঁ, তো প্রত্যেকে যেন ওখানে কানেক্ট হয়, তাদের মেল আইডি ওখানে দেওয়া থাকে।
ওকে স্যার।
So don't do this right now. Okay, don't do this. After my meeting, you can inform them. Okay. Shall I proceed? Shall I proceed?
জারি
Start my
জারি কল আসছে, একটু মিউট করে দে পাশ থেকে।
Okay, is it visible? This page?
Yes, sir.
Yes, sir.
This page also?
Yes, sir.
Okay, so right now I will start my lecture. So coming 30 minutes, I need to meet you all. Huh? I would like to meet you all. Huh? Mute all. So if you have any question, you can ask me after that. Huh? Clear? Clear to everyone? So I will start my lecture. Huh? Okay, so 8086 microprocessor, the first Intel 16-bit microprocessor, which was invented by the Intel Corporation in 1978. So it's first 16-bit microprocessor. And what do you mean by 16-bit microprocessor? 16-bit microprocessor means it can execute 16-bit data at a time. So according to the execution speed, so it executes the instructions within 2.5 million instructions per second, so that the execution time of one instruction will be 400 nanosecond. And in terms of the memory, like in case of 8085, the total memory space was 64 kilobytes. Yeah, 64 kilobytes. But in this case, in 8086 microprocessor, the total memory space is 1 MB. Now, how can you calculate the 1 MB total memory space? In 8086, the address bus is 20 bits, right? 20 bits. So number of address lines are 20. So according to the formula, that 2 to the power number of address lines is equivalent to the total memory space. So hence here 8086 has 20 address lines. So 2 to the power 20, which is equivalent to 1 MB memory space. Like in case of 8085, what was that? In 8085, the 16-bit address bus was present. 16-bit address bus. So address lines are 16. So 2 to the power 16, which is equivalent to 64 kilobytes. Yeah. So in this way, you can calculate the total memory space in any microprocessor. So here in 8086, that is 1 MB. Now another feature in 8086 is a very important feature, and that is it has 6-byte instruction queue. 6-byte instruction queue. So have you heard about the queue? Like you have heard about the stack. So in that way, queue is there. What is the function of that queue, or how the queue is operate? Now queue is operating in this way: the first in, first out. So which one? Suppose it's a structure of data. Now which is inserted into the queue, that will be processed first, and which is inserted last of this position, so that will be processed last. So it has this 8086 has 6-byte instruction queue. 6-byte means each portion, or each space is required to store 8-bit or 1 byte of data. So at a time, this 6-byte instruction queue can store maximum 6 bytes of data. Okay. So in 8086 microprocessor, why this instruction queue has 6 byte? Why its size is 6 byte, not the 7 byte or 4 byte or 5 bytes or any other in terms of size? Like in case of 8085, it was it has 3-byte instruction maximum, 1 byte, 2 byte, and 3-byte instruction. But in 8086, number of instructions length are from 1 byte to 6 byte maximum. 6-byte instructions are there. So to store one complete instruction within that queue, you need to store or you need to create the space to store such instruction, which is complete one instruction, which is equivalent to 6 byte. The length of that instruction should be 6 byte. So at a time, if microprocessor fetch the instruction and it stores into the queue must be maximum size will be available as 6 bytes. So one complete instruction will be stored into that space. So that's why the queue size in this case is 6 byte. And it has a higher execution speed because of the pipelining architecture. It has one architecture, one technology has been introduced in 8086, that is the pipelining. Pipelining architecture means two simultaneous operations are performed at the same time. Like in previous microprocessors, before the invention of 8086, how the instructions are executed. First instruction must be fetched from the memory, then it is decoded, then it is executed. The second instruction must be fetched after that, then decoded, then executed, then the third instruction. In this way, sequentially, one by one instruction will be fetched, then decode and execute. But in 8086, due to pipelining architecture, what happened? When the first instruction is being fetched by the processor from the memory and it stores into that queue, then from that queue, it goes to the circuit where it needs to be executed. Then when it is executing the first instruction, when the microprocessor executes the first instruction, side by side, the second instruction must be fetched from the memory and is stored into the queue. When the second instruction is being executed, the third instruction is being fetched. So when one instruction is executed, the second instruction must be fetched from the memory. So execution and fetching, these two simultaneous operations or parallel operation are performed at the same time. That is called the pipelining architecture, and it introduces this pipelining into 8086 microprocessor. That's why the processing or execution speed is much more higher compared to the previous versions microprocessor. Yeah. Now these are okay. Another thing is the operating frequency for 8086 microprocessor. Operating frequency for 8086 microprocessor. Uh, it started from 5 megahertz to 8 megahertz. The range is 5 megahertz to 8 megahertz. Yeah. And the operating voltage is same for 5 volt here also. 8086 to operate 8086 microburst. So these are the some features which I discussed. Then next I would like to discuss about the functional block diagram. Functional block diagram. So until this much clear to everyone? Until this much clear? Hello?
Yes, sir.
Yes, sir.
Yes,
The
sir.
feature, the pipelining, everything?
Yes, sir.
Okay. So next I would like to discuss the functional block diagram of the 8086 microprocessor. Okay. So I will start it. So I need to mute all.
Main out of three.
Okay. So this is the functional block diagram of 8086 microprocessor. 8086 microprocessor functional block diagram is divided as you have seen here in this diagram. The diagram is divided into two parts. Upper portion is called the BIU. Here, this upper portion is called the BIU, and BIU stands for bus interface unit. Bus interface unit. The lower section is called the EU section, which is execution unit. So EU stands for execution unit. Now, why this architecture is divided into two parts? Okay, so here one dotted line is drawn middle portion of this architecture, so that the upper portion and lower portion must be separated. So why this architecture is divided into two parts? Because of the pipelining architecture. Okay, so certain means here according to this structure, the upper portion that is to be connected to the outside of the microprocessor. Now outside of the microprocessor means what are the components can be present or can be interfaced with the microprocessor externally? The memories and the IO devices. Okay, so memories and IO devices are connected through this upper portion or called the BIU section, through this section. But EU has no external connection because EU that is used for execution purpose. So every decoding part and the execution part must be completed within this portion. So that's why the execution is within the microprocessor. So that's why it has no connection to the outside world. But BIU microprocessor needs to fetch the instructions so that it must be decoded and executed. So to fetch the data byte or any instructions from the memory, it must be connected to the external side, and to the external side the memory is connected. So that's why any instruction must be fetched in this way, and it must be transferred through this bus, and it stores inside this queue. So one by one, it has 6 byte instruction queue. So maximum 6 bytes can be stored. After that, when it is filled up by the processor, then one by one from this lower portion, it must be decoded within this block, that is the control unit block or control system block. Here the decoding operation must be performed, and from this position the required number of executions can be performed. So here BIU only fetches the instructions and stores into the queue. EU execution unit must be connected in such way so that it must be used to decode that instruction and execute the instruction. Okay, one by one. So when the first instruction is being executed by the processor, second instruction side by side must be fetched by the microprocessor, and it stores inside that queue. So that execution is performed here and fetching operation is performed here. So two simultaneous operations are performed at the same time. That's why it is divided into two parts. Upper portion, which is used to fetch the instructions one by one, and the lower portion, which is used to execute the instruction. Clear? So now, before discussing this block diagram in details, you must familiar with the memory space, or how the memories can be organized in 8086 microprocessor. Okay. So memory can be organized in this way. This one, suppose it is your 1 MB memory, total memory 1 MB. Now that 1 MB memory can be divided into 4 logical segments. 4 logical segments. Segments are called extra segment, code segment, stack segment, and data segment. Extra segment is written in this way: ES. Code segment can be represented by CS. Stack segment can be represented by SS, and data segment can be represented by DS. Now each segment, whether it is extra segment or code segment or stack segment or data segment, each segment has 64 kilobytes of memory size, 64 kilobytes wide. Okay, so total within that 1 MB memory space, anywhere these 4 logical segments can be initialized. Now each segment must be equivalent with 64 kilobytes memory space. So within that segment, you can store the data, or you can store the instructions, whatever, according to the segment of the function that can be stored. Now within that segment, each segment, some addresses are inside this segment, and these addresses are called offset addresses. Now for each segment, there must be some initial memory location from where this segment is started. Okay, and within that segment, individual locations are there, or addresses are there, which will be incremented by 1 when certain data byte must be executed. Now inside this address, the upper like for example, you have created your folder name and file name inside your laptop or desktop. Okay, so first you have to create the folder name, then inside that folder you have to create that file. Okay, so now if you would like to find out any document or anything else which is inside that file, first you need to go to the folder, then come to the file. Now here this folder represents this segment. Okay, within that segment or within that folder, certain files are available, several files are available. Now these files are called offset address. Offset. Okay, so the segments are used to store the segment addresses. Inside this segment, several addresses are there, which are called the offset addresses. Offset addresses. Clear? Like in this example here, in this example, so 8086, it has 20-bit address bus. 20-bit address bus. Data bus is 16-bit. Now 20-bit address can be represented in this way: 00000. Why this is 20-bit? Because each hexadecimal digit is equivalent to 4 binary digits. Like in case of 8085, the memory addresses are started from 0000 to FFFF. But it is here, the 20-bit address is represented in this way: 00000. 5 zeros will be there up to 5F. Each hexadecimal digit is equivalent to 4 binary digits, so that the address will be 20-bit in size. Clear? So this zero, like this zero, represent 4 zeros in binary. Second zero represent again 4 zeros in binary. Third zero will be again represented in binary. It is in 4 zeros form. Then the fourth number 0 can be represented in binary form as 4 zeros. So 4 plus 4 plus 4 plus 4 plus 4, it is 20. So 20-bit address is here. In this way, F can be represented as 4 ones. So one hexadecimal digit is equivalent to 4 binary digits. F represents 4 ones. Second F represents another 4 ones, which is 8 ones. Again, third F, it is represented in binary form 4 ones. So again, it is the total is 12. Then 4, 16. Then 4 ones, again 20. So 20 ones are here. So that's why it's a 20-bit address. Now in like microprocessor, so when any end user like you or me, whatever, we need to initialize the memory addresses in 16-bit in size, 16-bit in size, okay, not in 20-bit form. So every, all of you know that every memory address is 16-bit wide, 16-bit wide. So we need to initialize any 16-bit address, whether it is segment address or offset address. These are given in 16-bit form. The 20-bit address, which is generated internally by the processor. So using the combinations of that segment address and the offset address, combinations of these two type addresses, 120-bit physical address is generated. Clear? Another example, like you have one book. Within that book, you have 5 chapters. Each chapter has 10 pages. Clear? So 5 chapters are available. Each chapter contains 10 pages. Now page number 64. If you'd like to find out page number 64. So what is the process to find out that 64? Either you can search it from the page number 1, 2, 3, and all the way up to 64. Otherwise, you can go to the chapter number 6. Chapter number, suppose there are 6 chapters. Okay, suppose there are 6 chapters. Each chapter contains 10 pages. Then go to the chapter number 6 and page number 4. That is called the 64. Okay, so here how can you go to the 64? How can you calculate the 64? That is the page chapter number and page number. So chapter number and page number, the combinations of these two values, it creates your final value. Again, here in this case, this segment address and the combinations of the offset address, combinations of these two addresses creates a 20-bit physical address, which is the real address, actual address. Now here in this case, total 1 MB memory space is given as from 00000 to FFFFF. Within that 1 MB memory space, you can create any segment in anywhere, any segment in anywhere. Like in this example, the data segment is initialized from the 3000 memory address, 3000 memory address. So it maximum 64 kilobyte space is available within this data segment. So the last address of this segment will be FFFF. Clear? So it is started from 0000, then 0001, then 0002, then 0003, and all the way up to FFFF. So within this 64 kilobytes of memory location, you can use this memory location for storage purpose. Anything you can store it. Like in this case, for data segment, you can store the data. So your segment address is fixed, which is 3000. Within from this 3000, individual addresses are changed, and these inside addresses are called the offset addresses. So your segment address, actually it is the initial address of that particular segment, or that is the base address where the segment is started. So it is not changed. Your address, segment address, will be fixed. It is not changed. Within that segment, the 64 kilobyte memory locations are changed, and these individual locations are used as your offset address. So every time the offset addresses are changed within each segment. Okay, not segments are changed. So segment address is fixed. Within that segment, offset addresses are changed. Now for another segment like stack segment, so if it is started from 5000 memory address, so the last location of this will be FFFF. So actual 20-bit physical address for each segment, like for data segment, if it was started in 3000, it will be up to 3FFFF. Now how can we generate this 20-bit physical address using the segment address and the offset address? Okay, that's why here is your diagram. Here is your diagram. So every segment address must be stored in somewhere inside the microprocessor, and where it is, so you need some register to store the addresses. So that register size must be 16-bit in size. Okay, because every memory address is 16-bit in size. So whether it is segment address or offset address, you need to store these addresses into a 16-bit register. Now segment addresses are stored inside segment register and offset addresses are stored inside offset register. That's why within this diagram, 4 segment registers are there. ES for extra segment, CS for code segment, SS for stack segment, and DS for data segment. Clear? So if these are individual 16-bit segment registers, those are used to store a particular segment address or initial address of a specific segment. Like ES, this register can be used to store the extra segment address. Now uh, uh, segments are used in the memory which is outside of this processor. Okay, but that address should be stored inside the microprocessor within this register. So your extra segment is present inside the memory, but what is the address of that extra segment, that must be stored inside this register, which is extra segment register. Clear? For code segment register, so it uses to store the code segment address, which is 16-bit in size. Again, this one is your stack segment. SS represents the stack segment, which is used to store the stack segment address, and it is the DS, data segment, which is used to store the data segment address. Now these are used for segment address storage purpose. Now what about the offset addresses? Because every or each segment within this segment, individual offset address must be generated. So what about the offset address storage location, where it will be stored inside this processor? In that case, you need offset registers. And one of these offset register is so called instruction pointer, or IP instruction pointer. Now here these segments, now what is the function of each segment? Because each segment has its separate function. Like code segment, what is the use of this code segment? If you have initialized certain memory portion for code segment purpose, what is the use of that segment in memory? Now code segments are used to store or to write your instructions within that segment. Every instructions which you need to write or you need to initialize, that must be stored. Instruction codes are stored inside this in code segment. Okay, that is the use of code segment. DS segment, data segment, what is the use of this data segment? Only data can be stored within that segment. That's why it is called data segment. Extra segment, it is another segment which is used for data storage purpose. So that is the extended part of the data segment. So both data segment and extra segment can be used to store your data. Okay, code segment, that is used for instructions. And stack segment, what is the use of stack segment? So stack is a group of memory locations in RAM to store the structured data. Okay, your random data must be stored inside data segment or extra segment. Your structured data can be stored inside stack segment. So if individually all of these segments have certain or individual functions. Okay, so if code segment is used at a particular time, then segment address will be stored inside code segment register. In that case, what will be your offset register? Your offset register in that case will be IP only. If code segment is used as your segment register, then IP must be used for your offset register. These are fixed by the Intel. If you have selected code segment for your segment register, you must use the offset IP as your offset register. Instruction pointer will be your offset register. So your segment address will be stored in segment register, your offset address will be stored in offset register. So the combinations of code segment and IP, 120-bit physical address will be generated. Clear? And this 20-bit physical address generation happened in this block, which is called the adder block or summation block, adder block. Okay, now what is the significance of this structure? This is the arithmetic circuit. Now in any arithmetic circuit you need some inputs, so that after manipulation it generates some output. Here two input must be given in this way at the two side, and one output must be generated. So your code segment address must be given in this way, your IP address must be given in this way, so that the combinations of code segment and the IP, it creates a 20-bit physical address, so that actual address must be given to the memory device. Okay, now what is the formula of this 20-bit physical address generation? Write down uh, physical 20-bit physical address, which is equals to the segment address multiplied by 10h, h represents hexadecimal number system, plus offset address. I repeat, 20-bit physical address is equals to the segment address into 10h. So segment address must be multiplied by 10, and 10 it is represented in hexadecimal number, so that's why 10h. So segment address into 10h plus offset address. So that is the formula, so that 20-bit physical address must be generated, and this addition must be performed, or multiplication, whatever, every arithmetic operations are performed within this block. So that's why it has two inputs and one output. Clear? That is for code segment into code segment plus IP. What about the other segment addresses? If any, suppose if you have used the data segment for data storage purpose, or to fetch some data byte from the memory, you need to initialize the data segment address. In that case, if you have used the data segment as your segment register, what will be your offset register? In offset registers are here in lower section. 4 registers are called offset registers. These are stack pointer, base pointer, SI, and DI. Okay, so all of you must notice this. In EU section, execution unit section, lower section, there are 4 registers: SP, BP, SI, DI. Those are used in your as your offset register. So if you have used the data segment, in that case your data segment as your segment register, then offset register must be either SI or DI. If you have used the ES as your extra segment as your segment register, in that case your offset register should be SI or DI. If you have used the stack segment as your segment register, then in that case you have to use either SP, stack pointer, or base pointer as your offset register. Clear? So all these segment register and offset registers are fixed. You can't combine with any offset to any segment register. Like you can't combine the CS with SI or DI. You can't combine the DS with IP, or you can't combine SS with IP, or SS with SI or DI. No, these are already fixed. Segment register and offset register, the combinations are CS and IP, DS with SI or DI, ES with SI or DI, SS with SP or BP. Clear? So upper portion, in this portion there are 4 segment registers along with 1 offset register as IP, and the lower portion in this section 4 another offset registers are there. So all these registers are called special purpose register, because it has some special functions. So that's why these are special function registers. Now coming to this. So clear up to this much, this portion? So clear up to this much, everyone?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay. So after,
Yes, sir. Yes.
okay. Now within 5 minutes, the meeting maybe end, maybe end. So
3 minutes.
if it is ended without any notification, because already one a message has been already shown on your display, I think so. So if it is ended, again I will send you
Yes,
the
sir.
next meeting link within 10 minutes. within 10 minutes.
Okay, okay.
Okay.
Okay,
So
sir.
if this meeting ended suddenly, then I will give you 10 minutes to come again and use that link, and we will start the meeting again for 40 or 45 minutes.
স্যার এমনিতে
Okay, sir.
রিমেনিং 2 মিনিট স্যার তো আপনি লিংকটা শেয়ার করে দিলেই ভালো হতো এখন,
Sorry.
নাহলে মাঝে আবার ইন্টারাপ্ট হবে।
Because actually interrupt hobby, because there is no option to start without interruption. Okay.
আচ্ছা আচ্ছা, ওকে।
Either 1 minute, 2 minutes, 5 minutes, or 10 minutes may be there. Okay. So I will give you certain
2 মিনিটস আছে।
5 minutes I will give it. Okay. So that you can join it in proper time.
ওকে ওকে স্যার।
Okay.
Okay,
So
sir.
I will discuss the next thing, which is the 6-byte instruction queue. Okay. 6-byte instruction queue. Okay. So next is 6-byte instruction queue. The queue size is 6 byte because it is needs to store the maximum instruction as 6 byte. 6 byte. But not every time. There may be 1 byte, maybe 2 byte, or maybe 3 byte, or maybe 5 byte. So until when this queue is filled up by the processor, no instruction can be fetched further until the upper 2 bytes is free. Why upper 2 bytes is free? Because all of you know that it's a 16-bit microprocessor. Now 16-bit data can be accessed at one cycle. So if any 1 byte means 8-bit, any 8-bit is vacant, why microprocessor needs to waste such one cycle? If any 2 bytes are 2 bytes means 16-bit is vacant, so that microprocessor can take any 16-bit at a time. Otherwise, if it is only 8-bit is vacant, then one 8-bit is to be processed in one cycle. Then again, it needs to use the second cycle to fill up the next 8-bit. Okay. So no further instruction can be fetched by the microprocessor until the upper 2 byte is vacant or empty. What is the reason? Because the 16-bit microprocessor can transfer the data or can transfer